Hi, this is the next topic in BCC, Basic Concepts in Chemistry, and that too in a very primitive and outdated topic, that is laws of chemical combination. Those were the very prominent laws in 18th century when scientists did not know the formula of compounds, even molecules. Avogadro's was not propounded at that time. Nobody knew it is nitrogen, oxygen, all these elementary gases and diatomic molecules. Nobody knew that the formula of water is H2O. They were believing that hydrogen is H, oxygen is O, and when they combine, they produce a different substance, and that they were calling compound water, and they were giving a funny symbol. They call it symbol, not formula. HO, H plus O, HO. I think we did discuss that in our Avogadro's law topic. So at those times, these laws were very fascinating. We shall be discussing these laws only on historical grounds, to study how historically these laws are very important at those times. And to my mind, these should not be kept in the course in class 11. It should be discussed before class 9, just as a historical note that how the scientists were playing with the masses of different elements present in the compound without knowing their stoichiometry, the relationship between the elements, the ratio between the number of moles or number of atoms present in a molecule, so-called molecule. At that time, they were not used to the concept of molecule. So that's a compound, but what is the ratio between the atoms? They did not know at those times. So they were doing experiments on masses. Now let's, just for fun, we will be having this topic, not for your examination purpose. So you assure me not to be serious about this particular topic, but listen to me very carefully to know how these concepts were so much of significance at those times. In the 18th century, these laws had great importance, and at that time, chemical formula of substances, both elements and compounds, were not known. Now these laws have no significance and hence to be studied to understand their historical importance. These laws were formed the basis of Dalton's atomic theory and also the basis of stoichiometry. Right? That first law, the laws of chemical combination, was given by Lavoisier in 1773. Law of conservation of mass, particularly related to chemical reactions. Now the net mass will not change. Matter or mass cannot be created nor destroyed in a closed system. In a closed system. They performed many experiments, both chemical as well as biochemical, and they found that the total mass of the reactants before the reaction is equal to the total mass of the products after the reaction. So they were really amazed at that time that yes, Chemical reaction has happened, but no change in mass. That was a big surprise at that time. Many scientists joined, Landolt and others. They performed different experiments. Even a plant taken inside a bell jar with carbon dioxide, the content of carbon dioxide decreased with time. It was kept in sunlight, and but the mass of the entire setup didn't change, because even if the carbon dioxide amount in the surrounding vicinity decreased, but the mass of the plant increases because it produces carbohydrate by the photosynthesis. So, and also many chemical reactions. We are not going to discuss those things unnecessarily to kill our time. Now, the second law was in 1779, that is law of definite proportion, constant proportion or fixed proportion. At that time, when a compound was analyzed from different sources, for example, water was brought from river, from sea, from pond, from canal, to different sources, water was obtained and purified, of course purified, distilled, and they were found to have identical mass composition. That was their big surprise. They thought spring water might be having some greater proportion of hydrogen or oxygen by mass. So they found, to their big surprise, that the masses in water obtained from any source, different sources, was found to be fixed. So the law went like this. I say went like this. The law is like this. The same compound always contains the same elements combined together in the same fixed proportion by mass, constant proportion by mass. It doesn't depend on its source or the method of preparation. If the compound is same, it has the same properties, both physical and chemical, and they found to have the same elements combined in the same fixed proportion by mass. That is what is called stoichiometry. The relationship between the masses of the elements present in a compound, the ratio, and hence the atomic ratio, the molar ratio. When masses are fixed, the molar ratio is also fixed, and hence the atomic ratio is also fixed, right? Now, I'll give some examples. Water, not H2O. At that time, it was not known. I have just written. Water obtained from natural sources such as river, sea, spring, pond, etc. Or prepared by the combination of hydrogen. Not at that time, the formula of hydrogen was H2, not known. And oxygen, not O2, oxygen in language, always had a mass ratio of 1:8. In every 9 gram of water, 1 gram of hydrogen and 8 grams of oxygen was found. When 18 gram of water was electrolyzed, it gave 2 grams of hydrogen at cathode, 16 gram of oxygen at anode. I am saying 18 because we know the molecular mass of water is 18. But they didn't know that. They might be taking 100 grams. If 18 gram is giving 2 and 16, so you can well say if they would have taken 100 grams, then how much of hydrogen and oxygen would have been formed. But to make things clear, I am taking this just for fun. In the ratio 1:8, yes, but you can't say 18. How did you know 18? What is 18? But see, fun. Now we know the formula of water is not HO, it is H2O. So we know in 1 mole of water there are 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So that is 2 grams and 16 gram, and that is 1:8. You can prove this composition once the stoichiometry of water is fixed. Stoichiometry in a compound means the relationship atomic ratio present in that particular molecule. That is the stoichiometry of a compound, 2:1. And the atomic ratio or mass ratio is 1:8, right? So that has no significance now. Similarly, at those times they were getting 2 oxides of carbon. I'm not writing CO and CO2. Same oxide, but the same oxide, I'm not talking of CO and CO2. That will be discussed in multiple proportion law of multiple proportions. The same oxide obtained from many different sources, preparation methods. One of them is by heating limestone or chalk, which are calcium carbonate ores, minerals. So one of the methods of getting the same oxide of carbon is by heating limestone, and the other method is by burning coke or carbon in excess of air. So the sources are different, but the compound is same. How? The properties are same. So they analyzed per every 11 gram of carbon oxide. I cannot write carbon dioxide. On decomposition gave 3 gram carbon and 8 gram oxygen. I took 11 only because I know the ratio, mass ratio is 3:8. So I added up and took 11. And they might have taken 100 gram. Accordingly, you can say how many grams of carbon and how many grams of oxygen will be formed if 100 grams of carbon oxide, that oxide is decomposed. And the ratio always was found to be 3:8, right? Mass ratio. It's not the mole ratio or atomic ratio. It is the mass ratio. The elements are different, then the mass ratio is totally different from the mole ratio, as you know. Now it is funny to say it is 3:8 because we know the formula of carbon, that oxide which was referred to here, which was taken in this. It is carbon dioxide. Obviously 1 gram atomic mass, 1 mole of carbon is 12, 2 moles of oxygen is 32, and if you take the ratio it will be 3:8, right? So here is one typical experimental problem at those times. They were getting copper oxide, do not know what copper oxide, but the same compound, black, and properties are all same. Now they were getting by 2 ways. The first experiment was to take copper, to convert it to copper nitrate, and then strongly heat to produce copper oxide plus NO2 plus O2. So this is one way, and 1.5 gram was the mass of copper, and ultimately the copper oxide obtained was 1.875. So if you take the difference between the two, it will give you the mass of oxygen present in copper oxide. This is 1.5 gram and this is 1.875 gram, and the difference is the amount of oxygen present in this copper oxide. I am not writing, I have written here CuO, but they did not know it is CuO or Cu2O, that is cuprous oxide. They didn't know that. I am just writing because I don't have space to write in language copper oxide. In another experiment, they did it in a different way. They got the same compound, 3.4 gram of the hydrated copper sulphate, which contained 24.45% of copper. So 0.2445 into 3.4, that is the amount of copper present for which we are interested. We are not interested in sulphate or the water present in the hydrated copper sulphate. So 24.45% of 3.4 gram, we can get it. That was the amount of copper. And that, what happened, copper sulphate is first converted to copper hydroxide. I should have written in language, doesn't matter. You understand what I'm saying, so please don't mind if I'm writing in language, I mean formula, not in language. And then they strongly heated to get copper oxide. So mass of copper in hydrated copper sulphate, we already know it is given. It is 24.45% of 3.4 gram. We know the mass of copper here, the beginning. And now we have measured the dry oxide of copper has a mass 1.04. This we will calculate. And then take the ratio between the two masses. Here also take the masses of copper and oxygen. And bring one mass to one constant. So 1 is to how much? Supposing X. And here also you find copper to oxygen. Bring it to 1 is to Y. And this XY ratio, they got simple. They were excited that the same compound contains the same elements by fixed proportion by mass. So this X is to Y is not only simple but also in two different sources they are same. Is X and this I'm so sorry, this is not multiple proportion, simply the simplest ratio. Supposing here X is to Y, here it is M is to N, so X is to Y is equal to M by N. So I'm so sorry, there is no necessity to bring one mass to one or a fixed mass. That is in law of multiple proportion. Here the two ratios are absolutely same irrespective of the method of preparation or source from which a compound is obtained. If it is the same compound, then it must contain the same elements and the ratio between their masses is fixed, right? If the mass ratio is fixed, their mole ratio is also fixed, and hence their atomic ratio is also fixed. So stoichiometry, the formula is also fixed. Later on it was revealed, but at that time the mass ratio is fixed, right? Let us enter into another. So this I have already done it here. What we have written, this first copper oxide, the ratio between copper and oxygen by mass was found to be 4 by 1 or 4:1. And the second experiment, we took this much of copper, it's 24.45%, and ultimately we get this much of oxide. So minus this will give you this much of oxide, and minus this, that will give you the mass of oxygen. So again copper is to oxygen by mass is same, 3.976, that is 4 by 1. So the two ratios have to be same, and it became same, much to their surprise at that time, right? Here we have to make approximations, rounding off to the nearest whole number. If it is very close to a whole number, then we have to round off it. So experimental error is inevitable. So if it is 3.976, it can be called 4 because human error is always there. So the ratio was fixed. And now we can have many other compounds which are non-stoichiometric. So at those times they never knew that same ferrous oxide can have a formula Fe.950, not 1:1. It may be 0.95:1 or 0.92:1. So these are called non-stoichiometric compounds. And such compounds were not known at those times, and the stoichiometry is not fixed. If the ratio between the atoms in a molecule is not fixed, it varies. It's called non-stoichiometric compounds, right? So at those times, non-stoichiometry relationship was not established at those times. That is a demerit. Even now, we can take this as a demerit. Now later on we shall know that these non-stoichiometric compounds, sometimes this arises due to our efforts. We introduce defects, imperfections in a solid, and get the properties enhanced according to our requirements. We can tailor make the properties by introducing imperfections, right? Those things will be knowing in our solid state program. Now the second law is law of multiple proportion. It was propounded by Dalton, none other than Dalton. Hence it is also called Dalton's law. Dalton's law. The law goes like this. Let me read out. When two elements combine to form more than one compounds, different compounds, in the definite proportion, law of definite proportion, same compound, but different ways, different sources, different methods. But here two elements produce more than one compound. Then the masses of one element, which combine with the fixed mass of the other element, bear a simple whole number ratio to one another, to each other. So for example, carbon and oxygen, they form two oxides, oxide 1 and oxide 2. They didn't know at that time it is CO or CO2. Carbon oxide 1, carbon oxide 2. And by mass analysis, by decomposition mass analysis, they found the ratio between carbon and oxygen was 1:x. They kept one of the masses fixed, so 1 or 100 or 12, whatever. One of the masses to be fixed. Maybe the other one, maybe we can take oxygen fixed. Take any element, keep the mass fixed and find the other. So it is 1:x. And in other oxide of carbon, it was found it is 1:y. So the mass ratio of the other element, the varying mass, the element having varying mass, the mass ratio x:y is a simple ratio. So the masses of one element here, oxygen, which combined with the fixed mass of the other, here carbon, bears a simple ratio to each other. So this x:y is simple, means 1:2, 2:3, 2:5 and so on. Simple whole number ratio. Right? Obviously, when we know the formula of compounds, they contain simple whole number of atoms. So the ratios are bound to be simple. Have a concrete example, experimental example. Then we will see fun. Carbon and oxygen form two oxides. Oxide 1 on decomposition was found every 233 grams of that oxide gave 133 gram of oxygen and 100 gram of carbon. So we deliberately make the mass of carbon fixed. It could have been, instead of 100 and 103, this could have been 1 gram and 1.33 gram. Doesn't matter. In the other oxide of carbon, 100 gram of carbon, it may not be reacts with, contains 100 gram of carbon, combines with, we can say combines with, how could we know? We knew from decomposition of, say, 233 gram of that oxide, it produced 100 gram of carbon and 133 gram of oxygen. Combines with this much. So, and in the second oxide, 100 gram combines with 266 gram. That means every 366 gram of that oxide of carbon produced 100 gram of carbon and 266. It could have been 1 gram, it could have been 2.666 gram. So we have kept the mass of carbon here fixed. And if you take the ratio of oxygen, the variable masses of oxygen in the two compounds, you'll find it is simple. Obviously, see fun. We already know now. Then carbon has the oxide, two oxides, carbon monoxide and carbon dioxide. And there is one carbon here, one carbon here. So mass of carbon is fixed. 1 gram atomic mass supposing 12 gram. And here it is 16 and here it is 32. So 16 is to 32 is 1 is to 2. That is mass ratio. That was found experimentally at those times. Now we can look to the molecular formula and say for a fixed mass of carbon, the number of atoms are here same. So there is no need to reduce to the same number of atoms, and we found the atomic ratio is in the is as 1 is to 2. So the mass ratio will be in 16 is to 32, same as 1 is to 2, right? So since the mass, since the element is same, oxygen, so the atomic ratio 1 is to 2 that we know now is same as its mass ratio. 16 is to 32, that is 1 is to 2. Right? At those times it was very, very exciting when they found two different compounds and kept the mass of one fixed and found a very simple relationship between the other element and the masses of other element by mass, right? So this is another experimental example. Sulfur and oxygen gave two oxides. And in one experiment, one oxide formation, 2 gram of sulfur reacted with 2 gram of oxygen. So the ratio is 1 is to 1. And the other experiment, 3 gram of sulfur reacted with 4.5 gram of oxygen. So 3 is to 4.5. And here 1 is to 1.5. So we have kept the mass of sulfur fixed. We could have done the other way, kept this fixed 1 is to 1 and kept this as 1, and this would have come as a decimal point, decimal fraction. So any one can be kept constant during calculation. Once we find the masses of the two elements in a particular compound, a particular mass of the compound, then we take the ratio and can calculate the mass of the other when the first was kept constant in each case. So the mass ratio of oxygen, which combined with the fixed mass of sulfur, here 1 gram for example, is in the ratio 1 is to 1.5. So this is not a whole number ratio. Multiply by 2, then we get 2 is to 3, which is a simple ratio, whole number ratio, right? Now see the fun. Now we know, I'm sorry. Now we know the two oxides they were referring to are SO2 and SO3. So only one sulfur atom is there. So mass of sulfur is fixed, 32. So the masses of oxygen is 16 into 232, 16 into 348. So 32 is to 48 is again 2 is to 3. So the atomic ratio is same as the mass ratio if the element is same, right? And the mass of the other element is kept fixed here, sulfur. So that is very funny. Now see, at those times they knew there are 5 oxides of nitrogen. Now we know it is nitric oxide, dinitrogen trioxide, nitrogen dioxide, dinitrogen pentoxide. We know all this. But at those times, they just synthesized oxide 1, oxide 2, oxide 3, oxide 4, oxide 5. Now they performed the mass analysis by decomposition study or combination study, doesn't matter. So the mass ratio, this is the first element will be of nitrogen, second element will be of oxygen. So we have reduced the mass of nitrogen to be 1. The ratio 1 is to 0.571. Nitrogen to oxygen in the first oxide. The second oxide 1 is to this. Third oxide 1 is to this. Fourth oxide 1 is to this. Fifth oxide this. So if you take the mass ratio of all these mass ratio of oxygen, the element oxygen in all these 5 compounds, you get it is a simple whole number ratio 1 is to 2 is to 3 is to 4 is to 5. Now, while doing so, dividing, this is the smallest one is this, while dividing all others by 0.571, you may get some fractional values. For example, it may come 1.9999, for example. So that has to be rounded off to 2 because experimental error is always there. So if it comes 3.005, then it is 3, and so on and so forth. So they found that the mass ratio of oxygen, which combined with the fixed mass of nitrogen, is simple whole number ratio. I didn't have the emoji here I usually keep an emoji. How funny. So I have here made ha ha ha. Right? Once we know their formula, we know their oxidation state +1, +2, +3, +4, +5. So they will be definitely in the ratio 1:, this one nitrogen atom will be half oxygen atom. If you keep nitrogen fixed, then if for 2 nitrogen 1 oxygen, for 1 nitrogen half oxygen, here is 1:1. And here when 2:3 means 1:3/2. Here 2, 1:2. Here 2 is 5 means 1 is for 5/2. So if this is the atomic ratio, that also is the mass ratio. If you multiply by 16, that becomes the mass in 1 mole of it, which has combined with the fixed mass of nitrogen, and by divided by 16, it will be the same as atomic ratio, which has combined with the fixed mass of nitrogen, and multiply by 2, it will become 1, 2, 3, 4, 5. 2 will be cancelled. So, ha ha ha. Now, even at those times, they found many demerits after maybe some time. Now, ethane and propane, they had a mass ratio 1:this, 1:this. And if you divide, you won't get there so close that you cannot get, it came to 9:8. Is 9:8 a simple ratio? It's not. 9:8. And in the two compounds, decane and undecane, now we know the molecular formula of everything. The carbon is to hydrogen in mass analysis experiment. They found this, 1:this. And in undecane, it is 1:this. So the masses of hydrogen, which combined with the fixed mass of carbon, 1 gram, is in the ratio this. So when they're so close, then when you really perform some mathematical operation, you will get 121:120. Is it simple? Now we know the formula of decane is C10H22 and undecane C11H24. And if you keep carbon fixed, if it is 1022, 1, it is 2.2. And if it is 1124, then 1 is 24/11. And then try to find a whole number relationship between the masses of hydrogen in both the compounds, which are combined with the fixed mass of carbon, say 1 gram, that will be 121:120. Is it a simple ratio? Maybe whole number, but not a simple ratio. So, then the last one. I was just saying that these laws now, why now? In 19th century even, and end of the 19th century, and from 20th century carried no significance. We are studying only for historical significance. Now see that the third law of chemical combination is law of reciprocal proportion. It was in the last part, 1791, still in 18th century, right? Also called the law of equivalent proportion or law of permanent ratios. This law involves 3 elements and 3 compounds. I just compare in law of constant proportion, the first one. I mean, not the first, the second one. I've forgotten law of conservation of mass. So in law of definite proportion, 2 elements, but same compound. But in law of multiple proportion, that we just finished, two elements but different compounds. But here, three elements and three compounds. Now it goes like this. If element A combines with element B and also with C separately, A combines with B and C also combines with A. I mean B combines with A and C combines with A. A is a constant element, they fix same element, but B, C are two different elements combined with A to give two different compounds. Then if B, C will combine to produce a compound, then the proportion by mass in which they do so will be simply related to the mass ratio when B and C separately combine with a constant mass of A. For example, I am showing you this law in a triangular form to make you understand, to enable you to understand more clearly that supposing this element is A, this is B, this is C. We keep A constant. For example, you can keep any element constant mass. Supposing we keep A constant. So a compound between A and B is supposing AB. We don't know the stoichiometry. 2:1, A to B or A to B3. That is called stoichiometry. Fixed formula. Or AB5 or A5B. We don't know. Simply I write AB in language. And here a compound AC. Now, by mass analysis, we shall find for a fixed mass of A, what is the mass of B, and for the same fixed mass of A, what is the mass of C, to produce AB and AC, and take the ratio B is to C, which combined with the fixed mass of A. Keep that ratio. Then find a compound between B and C. This mass ratio is not from a compound between B and C. It is obtained from AB and AC, calculating the ratio B is to C, keeping the mass of A constant. And here the mass ratio is B is to C. In a compound between B and C is B is to C, right? And these two ratios, supposing here the ratio between B is to C is say X is to Y, here the same B is to C is M is to N. So these two ratios are either same, which is rarely the case, they are simply related. That means one ratio is a simple whole number multiple of the other ratio, or a simple whole number fraction 1/3, 2/3, or 3/1, 2/3 of the other. That means when you take the ratio of the two ratios, then you will get a simple ratio. That's what we mean simply related. And let me read out again. If element A combines with element B and also with C separately, if they can form AB and AC, if otherwise law of reciprocal proportion has no value. If A combines with B to produce a compound, A combines with C to produce a compound. Then when B, C combine with each other to form another compound, then the mass ratio between B and C in a compound of B and C will be simply related to the mass ratio when B and C separately combine with A to produce two different compounds, and the mass ratio between B and C which combined with the fixed mass of A, that ratio and the ratio when they themselves combine, they will be either same or they will be simply related, right? Now the same thing I'm showing here. A, supposing is the fixed mass, will be compound AB, and this is compound AC. So in BC, when you get a compound between B and C, the mass ratio B is to C, supposing X is to Y. And analyzing, calculating from AB and AC, what is the mass of B and C, which has combined with the fixed mass of A? It is this, M is to N. So these two ratios, they are simply related. These two ratios are simply related, which means, what is the meaning of simply related? The ratio of the two ratios is a simple whole number ratio. That means this is ratio 1, this is ratio 2. You can keep this in the denominator, or you can also keep this in the numerator, your wish. So the result will be a simple whole number ratio. That is the meaning of the two ratios being simply related with each other. You understand? So it carries little meaning here, because I will show you when this stoichiometry, the formula is known, then this is bound to happen. Now, this is an experimental example at those times. Now, sodium, and iodine and chlorine, this is the triangle. You can keep any one fixed. Let's take sodium as the fixed mass. So, sodium and iodine gave a compound sodium iodide. I am not writing the formula. I am not supposed to write the formula. And I am really amazed to find in many texts, even today, explaining laws of chemical combination, they are writing the formula. If you write the formula, then what is the meaning, the significance of these laws, right? Then from the formula itself, you can establish the laws. There is no point in that. There is no excitement in that. At those times, the formula were not known. Sodium iodide. And sodium and chlorine, they produce sodium chloride. And iodine also reacted with chlorine to produce iodine chloride. We don't know whether it is ICl3 or ICl or ICl5, doesn't matter. It can be anything. It can be anyone. So they took one out of many chlorides of iodine, they take one. I will tell you what they would have taken to substantiate these data. So in sodium iodide, they found the relationship between sodium and iodine mass ratio 1:5.52. And in sodium chloride, sodium is to chlorine is equal to 1:1.54. So we have kept the mass of sodium fixed. And then take the mass ratio between iodine and chlorine, which have reacted with fixed mass of sodium. So that is 3.58:1. Say it is ratio A or ratio 1. Keep it. And then analyze the masses between iodine and chlorine in a compound of iodine and chlorine. So that was found to be 1.19:1. This is one iodine chloride whose mass analysis was established 1.19:1. So this is ratio B, this is ratio A. So these two ratios are simply related because the ratios, the ratio of the ratios is a simple ratio. 3.58:1 by 1.19:1, that is coming, when you round off, it will be coming, it is 3. Exactly, it is coming 3:1. Sometimes you get 2.99997 or 3.01. So you round off, excusing to be a human error. That is a whole number ratio, right? Or else you can say this ratio is 3 times greater than this ratio. You can say that, but sometimes you can take it in the other side. But the sequence should be same. But you can take the other side. Then it is not 3 times. It is 1/3 of the previous one. So therefore, I love to say it is simply related. Even if I love to say, I really feel bad to teach these laws at this stage, class 11. But since it is in the course, in a majority of schools, even in the class 11 stage, I'm bound to do that. But I am really deriving pleasure while I share my experiences with these laws, not as a propounder of these laws, but as a teacher of these laws. How historical can it be, and how much honor those scientists, Dalton, Richter, Proust, Lavoisier, they commanded from humanity at those times. And C fun, I have copy pasted from some Google source. They have given the formula. This, supposing this is the constant element A, and this is B, this is C, right? They have written specific compounds between hydrogen and sulfur, S2S, and between sulfur and oxygen, SO2. It can be SO3. They have explained taking SO2, and also experimentally that was taken. Yeah, but these are not on the basis of their atomic masses, on the basis of their formula, on the basis of real mass analysis. But it is really funny, even in the text, they give the formula and they analyze the masses from their, atomic masses. There are 2 gram atomic masses of hydrogen and 1 gram atomic mass of sulfur. And they analyze in that way. That is very, very funny. As funny as these laws are to be taught at this stage. So, therefore, I wanted to impress upon these students who want a conceptual understanding that in these 2 compounds, S2S and SO2, H is to S is 2:32, and here O is to S. S is here. Is 32:32, right? So 32 is kept constant. I have cancelled these things, no meaning. So we have kept the mass of sulfur 32 constant, and see what is the ratio between hydrogen and oxygen. There's 2, hydrogen and oxygen, B and C. We found the ratio of hydrogen is to oxygen is 2:32, which have combined with the fixed mass of sulfur, that is 32. 2:32 means 1:16, right? This is ratio A. And when we get a compound of hydrogen and oxygen, our very favorite water, we did not know at that time it is H2O. Now we are writing in confidence it is H2O. So the mass analysis is 2:16. Very funny to write the formula and say mass analysis 2:16. They were really decomposing and finding the mass ratio, right? Is 1:8. So direct compound, the ratio is 1:8, and in direct analysis, the ratio is 1:16. So these 2 ratios are simply related, because the ratio of the 2 ratios is a simple ratio, 1/16 by 1/8. So 8 goes up, so it becomes 1/2. Hence, the 2 ratios are simply related. I think you understand. So there are many examples I have borrowed from the same source. Copper is, supposing copper, we take A, copper and sulfur, they combine copper sulfide, this cupric sulfide, we write the formula now, very funny. Copper and oxygen, we write cupric oxide, very funny. At that time, they were writing copper oxide, black, copper sulfide. And this is SO3. In the previous experiment, SO2 was taken. And in this experiment, SO3 was taken. Doesn't matter. If we analyze the masses from their molecular formula, though funny, it is, really stupefying. It's very rewarding for a teacher to convince the students. But I find there is no conceptual basis of the explanation. Because if you analyze from the molecular formula, there is always a simple ratio relationship in the molecular formula. The stoichiometry has been established. So what's the fun? So S is to O, it is 32:32. 32 in this case, copper is 1 atom. So the ratio of sulfur and oxygen masses will be 32:16. Here is only 1 atom, so 32:16, 2:1. That is ratio A. And in the compound SO3, S is to O is 32:48, 2:3. So these 2 ratios are simply related because 2/1 divided by 2/3, 2 get cancelled, it is 3/1. Ha ha ha. It is simple ratio. So it is bound to happen. if the formula is having a simple relationship, then these things will be bound to be simple. And there is another example. Carbon is, supposing A, carbon hydrogen giving methane. Supposing we do not know the formula of methane, carbon, oxygen, carbon dioxide. This is B and C. When B and C combine to form water, we'll find the same manner if one carbon atom is here. It is fixed. So H is to O is equal to 4 is to 2, that is 2 is to 1. Obviously, if the ratio is 2 is to 1 between atoms, the mass ratio is the same, because mass ratio is not same, but it is also fixed. So if atomic ratio is 2 is to 1, then its mass ratio will be 2 is to H is to O is 4 is to 2 or 2 is to 1. So 2, 1 means 16. So the mass ratio is 1 is to 8. So they were finding this. Later it was found the atomic ratio or mole ratio is this. Right? And between hydrogen and oxygen, the compound water, the mass ratio is 2 is to 16. Is exactly same. By chance, in this particular example, the two ratios are same. This is 1 is to 8 and this is also 1 is to 8. So they can be same or they may be simply related. So there are two more examples you can study. And this is an experimental example at those times. Ammonia, I didn't write NH3 because it was a practical mass analysis. Ammonia contains this much of percentage of mass by mass of nitrogen and the rest hydrogen. Water contains this percentage of oxygen and rest hydrogen. And nitrogen trioxide, I mean one oxide of nitrogen oxide of nitrogen contains 63.15% of oxygen and the rest nitrogen, right? From the above data, illustrate the law of reciprocal proportion. Now, it's very simple. In ammonia, hydrogen is to nitrogen is 17.65 is to 82.35. And let us keep H as A, fixed mass. So 1 is to this, right? The mass ratio between hydrogen and nitrogen is 1 is to this. And in water, here, see, the mass ratio is this is to this, so 1 is to 7.928. So we have kept the mass of hydrogen fixed. And the ratio, mass ratio between nitrogen and oxygen in these two compounds, which has combined with the fixed mass of hydrogen, is this is to this, is equal to 1.1699, say 1 is to 1.7. It is a ratio 1. And when nitrogen oxygen forms compound, say we have taken one oxide of nitrogen, whatever data was known at those times, it's one oxide of nitrogen. So 36.85 is to 63.15. So this is oxygen. So 1 is to this. Same, approximately same ratio here. Fortunately, the two ratios are same. If not, this would have been a double of that, supposing 3.4 or something, half of that, whatever. The two ratios are simply related to each other. Here they are by chance same. So that finishes our program on laws of chemical combination, and hopefully you have liked it. And again and again, I am not able to remind you about two things. And sometimes I am doing at the end. I should have done this in the beginning to garner more support from my viewers. I should have said in the beginning that, are you liking these videos? If you like, do not hesitate to just spend one moment extra time to click the like button. Does it take much of your time when you study till end, or you view and you liked it really, just click like button. Number 2, if you are continuously, getting benefit from our programs, then is it not worthwhile to subscribe to my channel? Subscription is not paying in any amount. I was having a notion, a wrong belief that subscription means paying. I was really scared of subscribing to any channel. But when I became a YouTuber, I found subscription has nothing to do with spending money, just to be a follower. That is here. It's maybe metaphorically, it may be used here. It's not a literal meaning, but do not forget to subscribe to my channel. Bye.